Okay, so for today, we want to keep using synthetic division, which we talked about our last class period. And we want to use it to actually help factor quadratics. And today, or quadratics, polynomials, right? They're going to be cubics mostly. But what we're going to see is that sometimes it's written a little bit different. So for this one, and this is on the back of our intro page. It's linked on the agenda. So if you know 1, 0, you can lower the degree of the polynomial to a more manageable problem using synthetic division. Suppose 1, 0 of the polynomial is x equals negative 14. Use synthetic division to, it actually should say factor, right? Or maybe solve for the x-intercepts or solve for the zeros. Just to kind of, the language there is not exactly as precise as I would like. So what we noticed is, hopefully with synthetic division, is every time if you had a cubic and you did synthetic division, right, your quotient was a second degree polynomial, right? Or if you started with a fourth degree polynomial and you did synthetic division, then you had a third degree polynomial, right? It just reduced the power. So for this one, now if x minus 14 is the 0, or x equals negative 14 is the 0, remember, that means that the factor associated with that would be x plus 14, right? That's our factor theorem, right? The 0, the factor. So we're going to put a negative 14 in the box. This is a little bit, probably more than I'd want you to do by hand, but we can make our way through it here. So if x equals negative 14 is a 0, what do we expect to see here for the remainder? 0, right? It should be 0. That's, if it's not, then it's not a 0. So we're going to bring down the 1, negative 14, negative 3, positive 42, that's negative 108. And then negative 108 times negative 14, that's a little bit tricky. The way I like to do that, even mentally, or maybe on paper, is instead of, so I have 108 times 14, right? I know it's a negative times a negative, so I'm going to get a positive here. The way I like to do it, though, is just think about, I use the distributive property to help me do math by hand if I need to, right? So 100 plus 8 is the same as 108, and 10 plus 4 is the same as 14. If we just FOIL it now, we're going to get 4 numbers that should be easy to add. So we get 1,000 plus 400 plus 80 plus 32. So that gives you 1480 plus 32 gives you 512. So that's, it's an alternative to doing the whole, like, the way they teach it, like in grade school. I kind of like to think about the distributive property. So then we get 0. So now, I think something that will really help kind of keep all this together is, as we're doing this, we found a factor, correct? We found that x plus 14 is a factor because the remainder is 0. Right? We know that division algorithm, if the remainder is 0, you're basically factoring. So at this point, let's rewrite f of x equals x plus 14, right? That's the divisor, times the quotient, which is x squared minus 3x minus 108. To keep writing this, and we're really going to shoot to get a completely factored form, because we know how to graph those, we know how to find intercept, we know all this stuff. Like you guys, you did a great job on the quiz for the most part, right? So now, with this, once we get to here, we can find the rest of the zeros, but we don't have to do synthetic division because this is a quadratic, correct? Once we get to a quadratic, you're either going to factor it or use the quadratic formula, or if it's like it only has an x squared, you could use square roots. But we should be able to solve a quadratic every time, right? Whether it's nice and it factors like this one, or whether it's kind of a pain and you have to use the quadratic formula and you even get some weird radicals in there. So to factor this further, we get the two numbers that multiply to be 108 and add to be negative 3 would be negative 12 and 9. Took me a minute to think about those, but we'll get x minus 12 and then x plus 9. Okay, so here we have, this is a completely factored form, correct? So for this, if you were asked what are the zeros of f of x, you could say negative 14, positive 12, and negative 9. Those would be the zeros of the function. If you were asked for the x-intercepts of f of x, you could say negative 14, 0, 12, 0, negative 9, 0. Right. Zeros and x-intercepts are very closely related, but there are some differences. Right? X-intercepts just talks about the graph, which is why we went ahead and put them as ordered pairs. And you'll have zeros that won't show up on the graph. If you get an imaginary or a complex number up here as one of your zeros, which we'll see, that's not going to correspond to an x-intercept. It's just a zero that doesn't show up on the graph. And then could you sketch this graph if you needed to? Then, sure. We know the intercepts, right? We know the end behavior would look like this. Right? We know the x-intercept is at negative 1,512, 0, which is kind of extreme, but we should be able to do that from here. So that's our goal, right, is to take a cubic or even fourth degree polynomial, get it factored down using synthetic division. Okay, so for our first example here, we had f of x equals 2x cubed plus 3x squared minus 39x minus 20, and we're told that f of 4 equals 0. And something I didn't point out enough before we tried this was that if 4 is a 0, the 0 is what would go in the corner for synthetic division. Okay, it's associated with the factor x minus 4. So it's important to realize, do you want to use a 4 or do you want to use a negative 4? If you're told it's a 0, you use that number. If you're told it's a factor, you find the associated 0, like from the factor theorem. So here we get 4, 2, 3, negative 39, negative 20. We do the synthetic division. If this is true, we have to get a 0 for the remainder, right? That was another property that we didn't spend a lot of time talking about with synthetic division is if you put a 4 in the corner here and do synthetic division, the remainder will be the same value as if you just did f of 4. Okay. Actually, synthetic division used to be used a lot for multiplying or putting numbers into big polynomials because it was easier than just plugging them in. Like if you had to plug in 4 by hand, it would kind of be a pain, right? If you had to work that out. Well, if you plug in 4 using synthetic division, it's not that bad, right? The answer is 0. So it's sometimes you'll hear it called synthetic substitution. Now, with the availability of calculators and it's not really a huge need anymore, but it is kind of a cool little trick, right? So the factor theorem is actually sort of a offshoot of this synthetic substitution idea. So x minus 4, 2x squared plus 11x plus 5. So to finish this now, at this point we have a quadratic, so we want to stop with synthetic division, and we either factor it or use the quadratic formula, or if maybe if we look at the next example, it only has an x squared, so we can solve it using square roots. Now, really important to get this completely factored form. So let's just look at this factorization just to review it. 2x squared plus 11x plus 5. This is what you might call a hard trinomial, or with a not equal to 1. If you need practice on these, go back and look at the, I think it's the A2 delta math. It's got be a not equal to 1 is the book for. So we need two numbers that multiply to be 10 and that add to be 11. And that's going to be 10 and 1. So we'll get 2x squared plus x plus 10x plus 5. Doesn't matter the order of the middle two, it'll work. So the first pair, I can take out an x. We're left with 2x plus 1. The second pair, we take out a 5, and we're left with 2x plus 1. This parenthesis has to repeat if it's going to work. So we put the outside pieces together, and then we put the 2x plus 1. So that gives us that our completely factored form is x minus 4, x plus 5, 2x plus 1. Now, it asks us for the zeros, right? So for the zeros, we get 4, 0, negative 5, 0. Be careful here on this one. It's easy to get lazy when you have these nice factors and just think it's always the opposite of the last number, but it's actually you're setting each factor equal to 0. So when we set 2x plus 1 equal to 0, we get x equals negative 1/2, which would give us negative 1/2, 0. Or, I guess it asks for zeros. We could have just listed them. These would really be our x-intercepts. Our zeros could be 4, negative 5, and negative 1/2. They're related, right? They're very closely related. So we doing okay with that one? Yeah? Everybody good? Okay, I wanted to look at the top right one, and maybe we'll just kind of run through the bottom, go over the answers the other ones. But this top right one has something kind of different that happens. It is f of x equals x cubed minus 9x squared minus 5x plus 45. And then f of 9 equals 0. Anybody notice anything about this original polynomial? Or did everybody just start with the synthetic division right away? Because that would be fine. It's what it told you to do. But if you notice, this is a cubic, right, with 4 terms. Sometimes they factor by grouping. Now that last one, if you tried to group it, it would not work at all, not even close to it. But here, if you look, it looks like the second term's 9 bigger than the first term, correct? And if you look here, this is 9 bigger, well, negative 9 bigger. Like 9 times 1, right, and this is 5 and 9. So this would actually just factor. Okay, just to consider that. You could actually just factor it by grouping. We'll look at that. But we're asked to confirm that this is a 0. So we can confirm that by using synthetic substitution or synthetic division. Same thing. Kind of a different use form. So I put 9 in the corner. And then we get 1, negative 9, negative 5, 45. We get 1, 9, 0, 0, negative 5, negative 45, 0. So we've confirmed that f of 9 is actually equal to 0, or that 9 is a 0. But let's look at what's left with our factored form. Would be f of x equals x minus 9, and then x squared minus 5. All right, so we get to here. Whether you did synthetic division or if you actually just split the middle and it worked, it would be fine. Now here, this doesn't factor over the integers. Like that's not. If it was x squared minus 9, we'd factor it, right? Or x squared minus 16, we'd factor it. This one we don't. So to find our zeros, remember we take x minus 9 equals 0, and that's where x is 9, but we knew that one. We were actually given that one. And then if you do x squared minus 5 equals 0, you get x squared equals 5. Here the key is don't forget you have to put a plus or minus when you square root. So we get x equals plus or minus the square root of 5. Okay, so these would be our 3 zeros. If you had to list your x-intercepts also, we would say 9, 0, radical 5, 0, and negative radical 5, 0. There's a rule, we haven't really talked about it yet, but it says that if you have a cubic, a degree 3 polynomial, you can have 3 zeros. It says you'll have exactly 3 zeros if you count the imaginary and complex ones and the repeats. It's a little bit more that we add, but it should be, typically you'll see 3 or, not always, but